made you co-host. So good morning, everyone. So Professor Sreekrishna of IIT-Guwahati will deliver the third lecture in this workshop. Yeah. So over to you.
Good morning, everyone. Thank you, Professor Abhijit. In today's lecture, we will try to cover hyperbolic geometry, and I will try to give you enough. So that you can probably do some calculations and some bit of discovery of properties yourself. So when a property is stated, maybe you can using this lecture and then some homework, you may be able to do some calculations yourself. So that's the idea. So why why hyperbolic geometry? So I will just quickly say, Professor Paul already mentioned it in the introductory lecture to this AIS. So I'll quickly say where this hyperbolic geometry fits in. Well, firstly, historically, hyperbolic geometry was, has its own interesting story. Using there were really contentions that the fifth postulate postulated by Euclid is actually redundant, etc. And so, in order to try to prove the fifth postulate using the first four postulates, the story goes that an alternative geometry was created where, in one form of saying, through a point and through a point which does not lie on a line, there are infinitely many lines which are parallel to the given line. Okay, so a new geometry was created. So and then this geometry on the plane is different from the Euclidean geometry that people realized. So today we are going to see what this different geometry on the same plane R2, topological plane R2 is. Okay, and firstly, what do we mean by another geometry at all? And then how different is this hyperbolic geometry? What are some of its properties? How does it differ from the standard Euclidean geometry that we already understand? Okay, so this is the this is what we are going to do in today's lecture. And where does hyperbolic geometry fit in geometry group theory? Well, what Michael Gromov has done is that he revolutionized the study of groups, well, in general metric spaces, by taking arbitrary metric spaces and giving, inspired by hyperbolic geometry, he gave a meaning to what a hyperbolic metric space is. So in particular, he took one defining one property of hyperbolic geometry, namely that triangles are thin. We are going to touch upon that towards the end of this lecture. So triangles are thin, and he applied that property to metric spaces. Whenever metric spaces satisfy that property, the triangles are thin, you can actually make sense of pretty much all of the machinery of hyperbolic geometry in the in metric spaces, in path metric spaces. So that is very useful when we study path metric spaces. For example, certain Cayley graphs of groups, they actually, with respect to some generators, they become hyperbolic metric spaces. So in discovering their properties, one needs to know hyperbolic geometry so that one can borrow from here and apply concepts there. So hence, this is an introduction to hyperbolic geometry that we will see. Okay. So let me start with the underlying set, the upper half plane. So I will first give a model for this hyperbolic geometry. So let's look at the upper half plane, namely the set of all xy in R2, such that y is positive. So we are looking at R2. This is the x-axis. This is the y-axis, and we are only looking at the upper half plane. And please note that the x-axis itself is absent. So this is y is equal to 0. So you're only having y strictly greater than 0. So it's an open subset of R2. This is not equal to. It's an open subset of R2. Okay. And H is also, it can also be viewed as, H can also be viewed as a subset of C, the complex plane. So we have a map from H to Z belongs to the complex numbers. Imaginary part of Z is strictly positive. Okay, and which basically maps xy to x plus iy, because y is positive, imaginary part is positive, and we can come back from any z in there in the set to here by this is the inverse by your real part of z, imaginary part of z. So as a set, and then this is the mapping from H to C and backwards. Okay, as I said, we have described H. So naturally, H gets subspace topology from R2. So H is a open subset of R2. So H has. So I will directly say that H then is a topological manifold. In fact. Manifold because it's an open subset of R2, which is and it's connected. So this is homeomorphic to R2. Right. So this is about the topological manifold. Now the next issue is of its differentiable structure. Since H is an open subset of the smooth manifold R2, so R2 also has its own differentiable structure. It inherits the differentiable structure, the standard differentiable structure of R2. So what this means is that you can actually put tangent spaces at points on H. Okay, so for the uninitiated, you have the space R2. So here is a picture of R2. So this is the point space. I have points labeled XY, X1, Y1, etc. So x-axis and y-axis are not the only support. In order to name this, you can have alternate coordinate systems on R2. So for example, you can have the spherical coordinate, or rather the polar coordinates. You can have other coordinate systems on R2. Now, at each point there, okay, so this is the point space. And for each xy in R2, you have a set of tangent vectors at that point. So there is a two-dimensional degree, the two-dimensional freedom there, right, to move. And then, so if you imagine a physical motivation for this is, if you imagine a particle at that point, there are R2 worth of velocities, possible velocities that it can acquire at that point. Okay, and the velocities themselves are not captured in the point space R2. Okay, so if you look at the point space R2, there is no information which tells you the velocity. Of course, what you do is you note the if the particle is moving, you note the next point. Take the difference between that point and this point and construct a secant and take the limit of that. You get a tangent vector. So you get basically basically the velocity vector, the instantaneous velocity at that point of a particle. So this is some motivation from physics. So which is why we model the as follows: for each xy belongs to R2, there is a collection of vectors, collection of R2 worth of vectors. So I will just put like that, R2 worth of vectors, velocity vectors, so to say, at excuse me, at this point x. So this particular collection of R2 worth of velocity vectors, those velocity vectors have the properties, the standard properties of vectors one studies in a physics course. So these velocity vectors, they form this collection form a vector space, which is isomorphic to R2 at that point x comma y. Okay, so this is the vector space R2 at xy, which is different from the point space. Okay, so I want to emphasize on this point that at each point you have this vector space. So what is happening is that at this point also there are R2 worth of vectors. Okay, so if you have already studied differential geometry, then you would have seen this construction. What we get is you collect all these vectors at each point of R2, so you get the tangent, the collection of tangent vectors at every point in the point space R2, the point space R2, in the topological manifold R2. This is your this collection is your tangent bundle. So tangent, because they are tangent vectors, so you get a tangent bundle. So it turns out in the case of R2, so this vector space has a name. We generally write it as R2xy, or as R2xy, or sometimes we also write it as Txy R2 to mean the tangent space at the point xy. The tangent space means that the tangent plane means that it is it is set of all tangent vectors at that particular point. Okay? And now this TR2 is collection of all such tangent spaces. So you get P comma V such that P belongs to the point space R2 and V belongs to R2 at that point. So it turns out I'm just asserting this is. It turns out that this is itself a manifold. I'm not proving it. Okay. So this is a manifold which is homeomorphic to R2 cross. Okay, so the collection of all vector spaces, okay, at each point. Okay, so that is a manifold homeomorphic to R2 cross R2. It's called the tangent bundle. This is called the tangent bundle. Okay. So then, yeah. So so this is called. So just for imagination, you can also think of the sphere. Okay, and then you all have done this in a multivariable calculus course. So the sphere, the tangent plane, the equation of tangent plane to the sphere, it will be basically perpendicular to the normal at that point, which is nothing but the radial vector. The normal is radial vector, so it will be perpendicular to that. So the collection of all these tangent planes on the sphere, okay, that is the tangent bundle for this topological space S2, for example. So it turns out that the tangent bundle on S2 is not S2 cross R2. Once again, I'm not proving it, but it is not S2 cross R2. Although the tangent plane is the vector space isomorphic to R2. Okay, so here because this is directly R2 cross R2, we call this bundle a trivial bundle. Whether you capture that word or not, I will just directly say that H, the tangent bundle of H, owing to the fact that R2's tangent bundle is R2 cross R2, the tangent bundle of H is TH, which is equal to H cross R2. So at each point of H, say Q, TQH, okay, is a vector space which is isomorphic to R2. So we have this collection of vectors at each point. Now we will look at, so why are we doing this? We are looking at plane geometry. So first we have this space H, which is homeomorphic to R2. So it is, well, in the world of topology, topological manifolds, H is nothing but R2. And when we put this tangent bundle, when we put the structure of tangent bundle on H, once again, you're getting TH is H cross R2, but as a manifold, this is nothing but R2 cross R2, right? So that is also R2 cross R2. So there is no difference so far. H is like R2. So this structure is called putting a tangent bundle. This is called putting a smooth structure on that particular H. So smooth structure on H, that is not different from the smooth structure on R2. So you get a manifold which is so-called diffeomorphic to R2. Okay, so that's what I mean by this sentence. Sorry. This sentence. Okay, so here I said that since H is an open subset of R2, it inherits the differentiable structure of R2. So basically, we have the tangent bundle, which is H cross R2. Now, the issue of geometry. So far, H and R2 are not different. Okay. Now the issue of geometry comes in. So plane geometry, we said that from history, H originated, the hyperbolic plane was discovered basically to create an alternative geometry. So far H and R2 are the same. They are the same so-called planes. Okay. Now, what about the geometry? What about the different geometry? Okay. So what does geometry mean to us? We have studied Euclidean geometry. Geometry means we will talk about lengths of curves, angles, okay, and then areas, okay, volumes in higher dimensions. But since we are only talking about plane geometry, we'll stick to areas. That's all. And then we talk about distances between points. Okay, so this actually is served by a metric. We know that we need a metric for that, etc. Okay, so this is what we mean by geometry. These are the aspects that we have to define for geometry. So let us go back to what we did for lengths of curves or angles, for that matter. So first, what we have is a in R2. So we have a, so once again, this is a point space. R2. Okay, and in that point space, we have a parameterized curve. So probably this is indicating the path taken by a certain particle. So it is parameterized means, so a parameterized curve. So it means that with respect to time, we are saying how it moves in space. So x of t and y of t are with respect to time t, they are capturing the motion of the particle. So, or the position of the particle. So at a time t, these are the positions given by the parameterized curve. Okay, and then alpha prime of t, we know how to calculate tangents. This is your x prime of t, y prime of t. Okay, and then this is a tangent vector at the point x of t, y of t. So at the position, so suppose here is the point x naught, x of t, y of t. Okay, so at this position, we want to know the instantaneous velocity of that particle, given that this was the this was the parameterization of the motion of the particle. Then we know that the tangent vector there, so I'll use, so the tangent vector there gives us the instantaneous velocity, right? So that's what we have. But at that point, we just said that there is a whole R2 worth of vectors. Okay, of all those R2 worth of vectors, this particular particle is taking up a single vector as its velocity by the virtue of its motion. So the motion is already here. Okay, by the virtue of its motion, it is basically taking up that particular vector. Now, so alpha prime of t is a tangent vector at the point. So it's actually, this guy is a is an element in t x of t y of t of R2. Yes, there's a question. So they are the same because the differentiable manifold C and the differentiable manifold R2. The question is that if we put the differentiable structure coming from C, what will happen? So the complex plane and the real R2, they have the same differentiable structure. So that's why there is no difference. Okay, so so now if you have well, you have this vector alpha prime. Okay, and then what we did to find out, yeah, so a quick example, I'll just jot it down. You can do the computations. So if you take the parametric curve cos t sine t, so suppose in the first quadrant, maybe at pi by 6, you have this vector at parameter t is equal to pi by 6. Firstly, what is the tangent vector? So this is alpha of t, alpha prime of pi by 6 is the vector minus half. So at the point half root 3 by 2 comma half, the vector that is chosen is this is minus half. Okay, so there are many other curves passing through this. I'll use another color. There are many other curves passing through the same point root 3 by 2 1 by 2. They will have their own tangent vectors, not this one, not necessarily this one. They'll have other tangent vectors. Okay, so that is the tangent vector. And then coming back to the length of the curve, so that example ends there, length of the curve of a parameterized curve alpha. So this is, as we know, is given by t is equal to a to b. So from parameter a to b, it is the norm of alpha prime of t. Right. So so in order to have a plane geometry, we need lengths, and for lengths, we realize that for a tangent vector alpha prime, we need a norm. Okay, so need a norm at each point. So we just don't need a norm on R2 at a point. So remember that we have TQ H2 H rather. Okay. So at each point Q, we need a norm on this vector space. So need a norm at each point HQ or at each Q in on PQH. So that's what we need for capturing lengths of curves. And what else? Angles. We mentioned angles. So recall what we did for angles between curves. So in calculus course, one learns that if you have two intersecting curves, there are tangent vectors, well-defined tangent vectors to these. And so the angle between the tangent is defined to be the angle between those curves. Okay. So, and then if you talk of angle between those vectors, you are now in the situation of the R2 at that point, at that intersection point Q. So these tangent vectors lie somewhere, and that angle, there is no predefined notion of angle in a vector space. So for that, if you have an inner product space, you can actually need inner product on R2. Need inner product on R2. Okay, so cos theta then is inner product of alpha prime, beta prime. These curves are parameterized curves, alpha and beta. So we need inner product alpha prime and beta prime. So alpha prime of t and beta prime of t are actually equal to the q. So rather, alpha of t and beta of t are equal to the q. So alpha prime of t, beta prime of t divided by the norms. That gives you so need an inner product. So once we have an inner product space, we can actually recover angle. Now, likewise, we also mentioned areas. So far we need this, okay. And we also mentioned areas. When we talk about geometry, we need areas as well. So how do you calculate areas? Areas, once again, this is I'll quickly recall the formula for that. Okay, this is x prime, x1 prime, y2 prime minus x2 prime, y1 prime, where the norm of this dx dy over the area under question. So what is this? This is basically you have x1 y1, a parameterized curve alpha. Alpha of t is x1 of t, y1 of t, etc. And beta is, sorry, I said curve, no, a vector there, a tangent vector there. Sorry. Okay, so you have x1 prime and y1 prime, x1 prime and y1 prime. This is a vector at a point, and x2 prime and y2 prime. So then you have a parallelogram going on there, and the cross product of x1 y1 and x2 prime and y2 prime, okay, y2 prime, they give you the area of that particular parallelogram. So if you have an area in on the plane, so by taking the estimating it by parallelograms, infinitesimally small parallelograms, and taking the Riemann sum, so over the parameter domain, this norm gives you norm of x1 prime y2 prime minus x2 prime y1 prime. This gives you area. So recall that this can be written as if I call this vectors x and y, by choice v1 v2. Okay, so I can recover this by square root of rather v1 v1. Okay, so you'll recall the parallelogram identity. Okay, so it can actually be v2 v2 inner product minus v1 v2 square. Okay, So the norm of this vector will basically be equal to this one, and dx. So that parallelogram identity actually recovers that that particular quantity being integrated. So here again we will need inner product. Okay, so this is absolute value, not the norm. Absolute. Okay, so this inner product is again needed. So I'll circle that again. So all in all, what I'm saying is that in order to calculate lengths, curves, the length of curves and angles and areas, we need a norm. Well, norm can be recovered from an inner product, and so even for areas we need inner product. So at each point, okay, so in R2Q, so at a point Q, so or HQ for that matter, or HQ, so if I take two vectors, this you would have done in maybe a linear algebra class. So B1 E1 plus B2 E2. So I'm taking the basis vectors as some E1 and E2. Okay, those are basis vectors. So I can write every vector in terms of those basis vectors linearly like that, and then the inner product of V1 and V2 by the definition of an inner product and using its properties, we can say that this is equal to A1 B1. So it's multilinear, right? So using the multilinearity, this is inner product of E1 and E1 plus A1 B2 plus A2 B1 times E1 B2 plus A2 B2 times. Okay, so at a point like that, Q, on the tangent spaces, we basically, so I keep changing the notation. By this I mean TQ of H. So the same tangent space. If we have two vectors like that, the inner product needs three quantities like that. If we have these three available, it gives us an inner product on that particular vector space. Okay, so these three need to be defined, and not only that. So if you take an adjacent point, so you are at TQH, and then you move to TQ prime H. Okay, so you need an inner product here. You need an inner product here. So I can take three different numbers here which define an inner product on this guy, and I can take three other numbers on here which define an inner product on this guy. But as I move from Q to Q prime, I require that these numbers vary smoothly. Okay, so if those vary smoothly and I have a smoothly, then I call this a smoothly varying inner product when I define such an inner product. So then I basically define what is called as a Riemannian metric. Okay, so a Riemannian metric is a smoothly very inner product on the tangent spaces. So at a point itself, I need three numbers to define an inner product, because this A1, B1, A2, B2, etc. They are coefficients of V1 and V2, arbitrary vectors. So if I just define those three numbers circled in blue or boxed in blue, then I define an inner product at a point. So how do I do that? So I define this by using a length element. This is the common practice. So I'll give a length element ds squared is equal to alpha dx squared plus beta dx dy, okay, plus gamma dy squared. When I give a length element like this, so what does ds squared do? It actually acts on two vectors, v1, v2 like this. So it basically takes alpha times, so this is at a point Q. At a point Q prime, so I will give a length element. When I define a length element, I will define three functions here, alpha, beta, and gamma. Okay, so these are 3 functions. So I want them to be smooth. So that's how I give a Riemannian metric. So let us see how this particular length element recovers an inner product at each point. Okay, so that's what I'm trying to do here. dsq squared v1 v2. So this is alpha times dxq squared acting on v1 v2 plus beta times dxq dyq acting on v1 v2 plus by symmetry it should be beta times dyq dxq acting on x1 x2 sorry v1 v2 and finally plus d gamma dy square acting on v1. So this is just a symbol. So alpha at a point q is a number, beta at a point q is a number, likewise q at a point q. Okay, so when I apply it at a point q, I have a vector space, whole vector space. I pick couple of vectors from there, and this is how it acts. So this gives me your alpha of q times dxq squared acting on v1 v2. So if I take these particular vectors v1 v2, so dx acting on a1 e1 plus a2 e2, that's the definition of dx. So that symbol dx, so it basically captures a1. So you get a1 a2, okay, plus beta of q, you get dx acts on v1 to give you, so this is tensor. So dx acts on v1 to give you a1 and dy acts on v2 to give you v2 plus, so likewise from this term you get a2 v1, etc. You basically recover an inner product of q v2. Sorry, this is a1 plus, so that was a2 v2. So this is a1 v1 and this is a2. I wrote a1 plus e1, right? So this is dx will capture this, dy will capture this. Dx acting on this will capture this, dy acting on this will capture this. So you get this particular expression, which is the same as this thing is the same as this thing. So with e1 replaced with alpha of q, etc. Okay, so specifying the length element hence recovers the inner product on tangent spaces. Now, so as an example, if I specify ds squared is equal to dx squared plus dy squared, okay, so then ds squared acting at a point q will give me on a vector applied to two vectors on a vector. This will give me dxq squared acting on. So let me make it act on v1 and v1 again. So this gives me v1 plus dy squared. So notice that in this example, the dx dy term is 0. The coefficient of dx dy term is 0. Beta dx dy. Okay.
So can you maybe explain the notation a bit more? I've never been very comfortable with this notation.
Which notation?
This ds squared and
so that is exactly what I've done here. So dx is basically, so when you say dx, it actually it acts on your R2 q at that point q and gives a real number r. What does it do? Dx actually, so every vector here looks like a1 e1 plus a2 e2, right? So dx acting on a1 e1 plus a2 e2 just recovers the number a1, etc. dy will capture the number. So that's the notation. Captures the number. Okay, so those are functions which actually act on this R2 q, vectors in R2 at the point q. Okay, so that's what I'm doing. So when I put E1, dx squared is basically dx tensor dx. So I have used the word tensor. So basically, the first dx acts on this, and the second dx acts on that, etc. So it will now basically, since both the vectors are the same, you get a square plus b square, where I'm taking v1 to be, or a1 square plus b1 square, a1 e1 plus a2 square. That's all it is. Okay. So you will recognize that ds now, if you take the square root, ds is nothing but square root of a1 square plus a2 square. This is the norm of the vector v1 in the Euclidean sense. Right? The Euclidean norm of the vector v1. So you can actually check that this particular Riemannian metric on R2, it basically recovers this Riemannian metric, recovers the Euclidean metric. Even the cos theta formula that I gave earlier, you can actually carefully check that it tallies with the angles that are given by your Euclidean angle, the usual Euclidean angle. Okay, so that's one example. Another example is, the current focus. The current example is your ds squared is given by dx squared plus dy squared by y squared. Okay, so here a ds squared acting on v1 at a point q, I must mention v1 v2 will give you. So I have to write v1 is a1 plus a1 e1 plus a2 e2, and v2 is b1 e1 plus b2. Then this will give you a1 b1 by y squared, where q is, so instead of q, let me write x comma y. Then this will give me x a1 b1 by y squared plus a2 b2 by y squared. So at a point x comma y, this is what it is. So since y is strictly positive, this is not a problem. We can divide by y. So this is on h, only on h. This cannot be naturally thought of as a Riemannian metric on R2 because y is 0 at some places. Okay, so this is a Riemannian metric on H. So I'm just declaring that that's a Riemannian metric. One can check that this recovers inner products, etc. Okay, one, I already said that this will recover inner products. So one can check that the angle coming out of this, angles are same as Euclidean angles. So, however, the lengths will be different. We will see in a moment. Okay, and now next we define the hyperbolic plane. So far we defined. So now we are formally going to state the geometry on the plane geometry arising out of this Riemannian metric. Okay, the hyperbolic plane. When we say the hyperbolic plane, we mean, so denoted by H2, is the Riemannian. So a smooth manifold equipped with a Riemannian metric is called a Riemannian manifold. So it's a Riemannian manifold H, GH, where H is equipped with, we already saw this H, it is the smooth manifold coming out of R2. This set is equipped with, this manifold is equipped with the metric, the Riemannian metric. So a Riemannian metric, as you see, is not a metric. So it's basically that expression. It's specified by a length element. It is actually a smoothly varying inner products on the tangent spaces. So that's what a Riemannian metric is. So a Riemannian metric, V squared is equal to dx squared plus dy squared. Okay, so i.e. this GH, this structure this it's acting on R2 cross R2 and giving you an R. So these are R2 at a point like that. Okay, and what it does is, so this is GHXY, H comma XY is, so this Q is XY, so this is XY and XY. So it's basically acting on two vectors like that. What it does is it takes V and V prime like that, and it sends it to 1 by Y squared times V prime, where by this inner product we mean the Euclidean inner product. So it's the standard inner product scaled by 1 by Y squared. So this is the new inner product at the point X comma Y. So that's what this G does. So the collection of all these inner products is given by this. Okay, it is also given by this particular length derivative. So that's what is an hyperbolic plane. So it is a Riemannian manifold equipped with this metric. Okay, now I will talk about lengths of curves. So after all, that gives us geometry. So what about lengths of curves? So let gamma from AB, H to be a curve. Then the length, the hyperbolic length of this curve is basically A to B. The hyperbolic, so this defines a norm. If I take V prime to be equal to V, I get 1 by Y squared inner product of VV. And so the norm of V is defined to be, so this H2 norm is defined to be square root of this. So it's 1 by Y inner product of V, the standard Euclidean inner product of V. Okay, so the hyperbolic norm of gamma prime of T. Okay, this is your entity. So this is some positive number, it's an aside, but this gives the hyperbolic number. So this is an item number I'm creating. Okay, so that's length of curves. Okay, so using this length of curves, we can make an estimate. So here is an estimate. So it's a good practice to basically calculate length of few curves using this this knowledge that you have. So using this particular inner product, etc., you can actually try to calculate the length of few curves. Okay, so here's an estimate. Let gamma. So this particular, I must announce that this particular Riemannian metric, because of all the geometric aspects we covered earlier, it defines lengths, we define length, okay, lengths of curves, it gives us angles, it gives us areas on the hyperbolic plane, etc. Okay, so here is a estimate on lengths of curves. So let gamma AB to H be a smooth curve. And let me call m to be the little m to be the minimum of all the imaginary parts of gamma of T, such that T belongs to AB. Okay. And capital M to be the maximum of the imaginary parts of gamma of T, T belongs to AB. Then it's true that 1 by m and the length according to the Euclidean metric. So D is Euclidean metric here. So this is less than or equal to, or sorry, this is actually greater than or equal to the hyperbolic length of gamma. Okay. and this is in turn greater than or equal to 1 by capital M, the Euclidean length. Okay, and this is in turn greater than or equal to 1 by M times, I'll write below. This is in turn greater than or equal to 1 by capital M times the Euclidean distance between gamma of A and gamma. So this is an estimate which is useful in explaining certain facts. So so let us take examples instead of proving this proposition, which is an easy calculation, by the way. You have the length formulas, or you take a parameterized curve and try to do some estimates. Okay, so it's a straightforward estimate using integrations. But what I will do is an example. So couple of examples, if you will. So I will take a so here is H. I'll take a horizontal line like that, line segment. Okay, I need a parameterization. So let me say that this is gamma 1. Okay, so gamma 1 is of T is given by T plus Ci. So this is this height, this Y height is C. T plus Ci. So it's a horizontal line in visually in the upper half plane. Okay. So gamma 1 of T, and then I have to specify T. So these beginning and ending points pertain to 0 and 1. So it's a linear parameterization like that. So what is the Euclidean length of this curve? Well, it's simply straight away 1, right? And then what about the hyperbolic length? So it is from 0 to 1, 1 by y. So the y coordinate is c. So you get 1 by c when you take the norm. It's not y squared, but 1 by y. Right here, 1 by y. And then gamma 1 prime is 1. Okay, so here you just get. So square root of 1, so you get 1. Okay, and norm of that is just simply 1. And so dt, so you get 1 by c. Okay, so likewise, so here you notice that the imaginary parts, so little m, I'll not write the this thing. It's amply clear. Little m is equal to 1 or c. Capital M is equal to c. Okay, so you have 1 by c is that inequality. Verification is nothing but it's 1 by c times 1 is greater than or equal to 1 by c is greater than or equal to 1 by c times. Right? It holds. And what about the distance between those two endpoints? That anyway, the Euclidean distance is also 1. So this is greater than or equal to 1 by c. So actually, in fact, equality holds in this case. Okay? And I said a couple of examples. The other example is basically you take a vertical line. Okay, parameterize it as gamma of t is equal to a certain c. So this is on the this point is c comma 0 on the x-axis. When you project it, of course, c comma 0 is not in h. Okay, it's basically a parameterization like this, c plus ti. Okay, so I'm using complex coordinates. Okay, and then t varies from 1 to 2. I cannot take 0, 1 to 2. Okay, so if I take this, the length, the Euclidean length is anyway 1, right? And then what about the hyperbolic length? So you get LH2 of this gamma is integration from 1 to 2 of 1 by t. Y is t now. Okay, and then square root 1 anyway. Okay, so when you differentiate, you still get 1 and the norm is 1. So this will give you ln of between 1 and 2. So this is ln. Okay. So the length of this is ln, whereas this one is 1. Okay. Okay, and what about little m? Little m in this case is the maximum, is the minimum imaginary value, which is 1, and capital M is 2. Okay, so in this case, the verification looks like verification of that identity, or sorry, inequality in that proposition will look like 1 times 1 is greater than or equal to ln2. Okay, is greater than or equal to 1 by 2 times 1 is greater than or equal to the Euclidean distance between these 2 points is anyway 1. So this is 1 by 2 times. So that's fine. Okay, so that is a useful estimate in proving the following proposition. So we have next proposition. Let gamma from AB H be a smooth curve, and let P be I times imaginary H. So from I times imaginary H to H. So this is a projection, be a projection. Okay. So you basically, what I mean to write here, I will say that P be a projection. Let P be a projection onto imaginary axis. So if you have a curve like that, you project everything to, that's the projection map. Okay, and then the hyperbolic length of a curve gamma is greater than or equal to the hyperbolic length of the projection of gamma. Okay, and then and equality holds if and only if real part of gamma is constant. So equality holds if and only if the real part of gamma is constant. So real part of gamma is constant means that this curve is a vertical line. So this is a straightforward verification. Okay, you can actually use setup integrals to prove this. Okay, further, just note that gamma should be smooth. Okay, so that's the hypothesis. Further, the length of the hyperbolic length of the projection is greater than or equal to, once again, some calculation, the log of the imaginary part of gamma of B minus the log of the imaginary part of gamma. Like some calculations we saw above, this can be proved. And equality holds if and only if the differential of the imaginary part of gamma. So imaginary part of gamma is also a function of t like that when you parameterize, does not change its sign. Which means the curve should not go up and down like that. So then the equality actually comes. So that's another estimate which will help us capture the fact that, I mean, I'm just giving these propositions because they'll help you in proving that vertical lines are actually geodesics. Okay, so I'll talk about geodesic. Geodesic is what is it? It is the following. So firstly, metric. We left out one thing in this list. Sorry, let me go back. In this list, we did not talk about distances and metric. So we saw that Riemannian metric is not a metric. Sometimes, beginning students' confusion. Okay, it's a smoothly varying inner product on tangent spaces. Now, does that actually define distances? Does that define metrics? Yes, you can do it if you define it as follows. So metric, you can talk of a metric on, just treat this as a metric space and define, if you take Z and Z prime in H cross H, okay, so you define the distance between them to be the infimum of the lengths of all curves, smooth curves, gamma is smooth curve with, or I'll just say from Z to Z prime. Okay, so otherwise I have to mention the parameter interval, etc. So it is starting at Z and ending at Z prime in the direction of the parameter. Or the other way, this is symmetric, so then DH is a metric. So I will leave the verification. I'll just say that DH is a metric on okay. So so first I will make many assertions. So you can actually demonstrate that DH is a metric by examining symmetry is not a problem because it's infimum like that. Okay, and then symmetry is not a problem. The other triangle inequality, etc. You can actually use certain smooth curves from X to Y, Y to Z, concatenate them, and try to prove triangle inequality. And the fact that the distance from a point to itself is actually equal to 0. Okay, that also can be proved. Okay, and then the topology induced by this metric. Once again, easy check. Topology induced by this metric is same as the topology on H. Okay, so and then so this defines a metric. So there is a notion of the metric length. So what you can do is, so before I announce this theorem, there's a notion of metric length. We just defined lengths of curves, right? So if you take any curve, you can, if you have distance like this, you know, or otherwise, if you have a distance on it, what you can do is you can actually take distances like that of prop points. Okay, and then you can actually sum up those distances, and you take more and more points and get an estimate of the length of this curve. Okay, so all you're basically doing in the smooth category, you're basically capturing the tangent vector. But if you just have a metric without the support of the differentiable structure, then you can also capture this kind of metrical length. So this can be defined as if gamma is this curve. So it's basically the supremum of, so you take the lengths estimated by this, the distances, okay, and then the supremum of the set J is equal to 0 to K minus 1. So you sum up all the distances. So DH gamma of Tj, gamma of Tj plus 1. So this is T0, T1, T2, so on, Tk. Okay, and then this is the distance between that such that K is in N. So you divide more and more T0, so on, and Tj belong to this parameter interval AB, where so gamma is from AB. Okay. So so actually this T0 is equal to A. Okay, so T0 is equal to A and Tk is equal to A. Okay, so so first we have a theorem. It says that the hyperbolic length, arc length that we defined, actually tallies with is same as the metric due to. It's the same as the metric length due to village. Okay. And then we have a proposition using this. I'm not, once again, for lack of time, I'll not prove these propositions. I will just announce that this will allow us to prove vertical lines are actually geodesics. What is a geodesic? So when you have distances, there is a notion of smooth curves whose length is actually equal to distance between those 2 points. Okay, so if there is such a line, then you call that a geodesic. So and then the vertical lines you can actually capture are geodesics using this, okay, using these propositions. So now, so we at least get vertical lines, okay, and then we are also going to show, so these vertical lines in the edge. Notice this is absent. The x-axis is absent, right? It's only these vertical lines. So they are doubly infinite in the sense that here they don't touch the x-axis, and upstairs they go on until infinity. Okay, so they are doubly infinite in that sense. Okay, and notice that this going back to this definition of hyperbolic plane, this inner product is such that it is weighed down by y squared. So vectors downstairs, when they are 1 by y squared is very large for small y. Okay, so vectors appear to be small, but they are actually very large. Okay, so to the visual, to our eye in R2, they appear to be small, but the vectors are very large. Also, curves appear to be small. I'll exemplify here. When you take a curve like that, you can actually calculate and show this thing, that you take a curve which is somewhat like that, a small curve like that, and then a large curve like that. Although this appears large to our eye, this curve and this curve will have comparable length. Okay, so of course I did not draw it to any scale, but a small curves there will have great length. Okay, so I will announce that we are going to see using isometries, okay, that now we prove vertical lines are geodesics. Then there are semicircles which are centered at circles centered at points which are on the real line. So they give you semicircle when you intersect it with H. So these semicircles, small or large, these semicircles along with these vertical lines, they give you all geodesics in. So in particular, so we are going to see this, okay, and then in particular, if you take 2 points like that in the hyperbolic plane, then it's not, the Euclidean distance would be along this particular straight line, but the hyperbolic distance between these 2 points will be different, potentially different, but it will be achieved along a semicircle which basically contains these 2 points. Okay, the construction of such a semicircle is easy, but yes, there will be a semicircle connecting those 2 points like that. And if they are vertical, you can't construct a semicircle, you can do a straight line like that. But that will achieve the achieve the distance. All right. So in order to do or see that these other lines are also geodesics, we first need to get to see the isometries of this particular plane. Okay, so this geometry that we captured. So firstly, a Riemannian isometry of H2. So I'll define it in the limited context of H2 is a smooth. So please excuse me, I'm switching between notations H2 and H. They are one and the same. So, so this is a smooth diffeomorphism F from H to H. So this is the set. This is the smooth manifold H. So it's a diffeomorphism of the smooth manifold. So I assume you know what that diffeomorphism means. It's basically not only is it a bijective homeomorphism from H to H, but the differential df at each point Q of H2, that differential takes the vector space. So df at each point Q takes the vector space PQH to Tf of Q of H. So the Jacobian transports the vectors, and that Jacobian is a isomorphism of vector spaces. Okay, so not only is F a homeomorphism, but this is also this requirement is also there for a smooth diffeomorphism. That's what a smooth diffeom, and it has an inverse. So DFQ is an isomorphism. So by inverse function theorem, you can actually get a inverse function on F in charts, and then you can assemble the charts and you get a smooth structure. Sorry, a smooth inverse for F. Okay, so that's the idea. And then this definition is that it is a smooth diffeomorphism. I'll erase all this stuff. Smooth diffeomorphism carries that information, and that satisfies the following property for all Q in H and for all vectors VW at the point Q. So they are in the tangent plane TQH. The inner product, the hyperbolic inner product DFQ at V, okay, and D applied to W, okay, at H2 is equal to the inner product of V and W, of course the H2 inner product. H2 inner product means it is 1 by y squared, etc. So at the point Q. So this is at the point Q, and this is at the point F of Q, because DF transports vectors from the tangent plane at Q to tangent plane at F of Q. So this inner products should be agreeing, and then you call this morphism, this particular map, which is already a smooth diffeomorphism, a Riemannian isometry. So these are the correct automorphisms, the right automorphisms in the category of Riemann surfaces. Okay, and then this naturally, like we announced in the first lecture, this will automatically form a group. Okay, so group, we'll denote this as isometries. So next we will bring in Mobius transformations and show that that has some bearing on this isometric group. So as of now, it's just some, just this definition. We have no handle on it, right? So we are going to bring in Mobius transformations. Of course, I'll not be able to do this elaborately. We are just going to show that Mobius transformations define some maps on the hyperbolic plane H, and that will actually become an isometry of H. And then we'll announce that, so we'll announce something. So here is A, B, C, D. So what are Mobius transformations? If you take an element in SL2R, a matrix in the group SL2R, the matrices, 2 by 2 matrices with real entries with determinant 1, they map from fold H. So there is a map which is Fa of Z is equal to Az plus B by Cz plus D. So you might have looked at this Mobius transformation. Okay, so there are so please look at the properties of these Mobius transformations. Then I'll write a few imaginary part of Fa of Z is going to be 1 by Cz plus D squared, the modulus of that times imaginary part of Z. Then the map defined by identity is the identity map on H, and this is the map defined by minus identity matrix. And the third property is that if A, B are in SL2R, there are FA and FB defined by it. Then there is also a map defined by F of F A times B. Okay, so this tallies with the composition FA composition. So that's the nice property of this. All these are very easy to verify, right? And then you have some particular maps. Okay, so let us look at A subscript B. This is the matrix 1B01. This corresponds to the FAB. What will this be? This will be Z goes to Z plus B. So this is Z plus B. So what this map does is that if you take the hyperbolic plane, so this is H, then it takes a point and transports it by B. Notice B is a real number. This is coming from SL to R. Okay, so B is a real number, so you add a real number B to the only to the X coordinate here. So you translate. So everything translates by B. Okay, so in particular, a vertical line like this moves by a distance B. Okay, that is FAB. And then there is the matrix 0, 1, minus 1, 0. This is the map. So the FB is going to be of Z is going to be minus 1 by Z. Okay. So this once again you can see it preserves the unit circle and vertical lines like that. Okay, this point. So here is 0. This is 0. So infinity travels to 0, and vertical lines like that. This point goes to minus 1 by this real number. So this guy comes to something like this, and so the image of this will be a line like a circle like that, and the image of this is a circle like that, or maybe smaller actually. Depends on its magnitude, so it will be smaller. So this comes there, etc. So you can study the properties of this, and AB for B belongs these generate SL2R. It's a fact that these generate SL2R. Okay, and here is basically the important fact. What is the relevance of this to the hyperbolic plane? The Mobius transformations, okay, are isometries. So these are basically, so at least you saw that, you know, well, I didn't yet say that the semicircles are geodesics. I just announced them. Okay, I said that we will see that. So Mobius transformations are actually isometries. So this is a proof one needs to do first. So FA belongs to isom of H. So you can check that. This actually FA is a map from H to H. You can check that defined like this. FA is a map from H to H. You can check that this is a smooth map. It's a Pipiomorphism from H to H, okay, for any A, and you can actually verify this fact, this particular equality. Okay, so compute that differential, and look at how it maps to vectors. And so it's an easy exercise in calculus. Okay, so you can actually show that FA belongs to isometrics of H2. Okay, and geodesics in H, dH. Remember, there is also a metric going on H, defined by infimum of lengths of smooth curves. Okay, connecting 2 points. So these geodesics in HDH under this map FA, they go to geodesics. One can show that using that formula for distances, one can show that geodesics go to geodesics. Using this, you can actually capture that if you take a vertical line, it maps to a semicircle like that, and hence these also become geodesics. Okay, so using that fact, you can capture that all semicircles with center on the real line, they also are geodesics. Means that two lines don't intersect. So if you take a line and a point not on that line, you have infinitely many straight lines passing through that point which are parallel to this given line. Okay, so that's your hyperbolic geometry, which is not true in the Euclidean geometry case. And then one actually discovers that, for lack of time, I'll just say this. PSL to R, we saw that F identity and F minus identity, they both give you the identity on H. Okay, so PSL to R, so you quotient the SL to R by identity minus identity, the Z2 group, identity minus identity. This will give you all the orientation preserving isometries of the Riemannian manifold H2. Okay. Now, some properties. Okay, I already announced what the hyperbolic geodesics are. So these are geodesics. What are geodesics? Basically, all the semicircles and all the vertical lines. Semicircles centered at the centered on a real the real line. Okay, so PSL to R, by the above functions F that I defined, they act transitively. This group now acts transitively on the hyperbolic. Okay. So, and then there is more to this than this one. Okay, by the way, this proof is not hard. It's just lengthy. One can refer to Anderson, hyperbolic geometry. That this is actually isomorphic. And we left the question of, so we talked about lengths of curves, we talked about angles. We said that the angle recovered from this Riemannian metric will be the Euclidean angle. But what about areas? In connection to areas, we have the Gauss-Bonnet. Once again, it's just going to be announcement. I will say that if you have a hyperbolic triangle made of 3 semicircles like that, that's how it looks, made of 3 semicircles. So, or here, look at in the upper half plane, well, not really 3 semicircles. 1, 2, and this one. So here is a triangle. Here is a triangle. Okay, or yeah. So the Gauss-Bonnet theorem asserts that the area of a triangle is actually equal to pi minus the sum of the angles alpha, beta, and the angles. So I'll blow up this picture to show that, to indicate alpha, angle beta. If you take angles alpha, beta, gamma, then the hyperbolic area of the triangle is simply pi minus alpha plus beta plus. Okay. So we did a lot of this hyperbolic geometry in the upper half plane model. What we have is H along with this Riemannian metric. There are alternate models of the same geometry. You capture the same properties, the same geometric properties. You can often refer to the Poincare disk model. In here, you basically take the unit disk and equip it with the equivalent metric, Riemannian metric rather. Okay, and so notice firstly that you are only taking the open unit disk. Okay, so that is also a plane. It is homeomorphic to a plane. It is in fact open subset of R2, connected open subset of R2. It's actually diffeomorphic to R2. So now with the standard definition inherited from R2. Okay, so you can put a Riemannian metric on it. I'll not have time to discover the Poincare disk model. Okay, so one last important property that basically led Gromov to define hyperbolic metric spaces in general is the following property of hyperbolic triangles. Hyperbolic triangles are slim. What this means is that there is a constant C, okay, such that there is a universal constant C such that every geodesic triangle, so triangles made out of straight lines, geodesic triangle. In hyperbolic world, straight lines are the semicircles. In the metric space HDH, now by above we know that this is the hyperbolic plane, like we defined, is C slim. It has the following property for every triangle, geodesic triangle. So it's made out of 3 straight lines, like I have pictured here. So gamma naught from 0 L naught to H, gamma 1 from 0 L1 to H, okay, and for every T belongs to 0 L naught. Okay. There exists a S in 0 L1. So this is the domain of gamma naught. Okay, there exists an S such that the hyperbolic distance and then gamma 1 of S point. Okay, so there is a whole there's a point S here such that this whole side is at most a distance C from there, and that holds for any other sides. Yeah,
I think this should be odd. I mean,
sorry.
So for all T, there exists S either in 0L1 or 0L2.
Yes, or 0L2, is it?
Yeah, not and.
Or.
Yes,
yeah,
correct.
Correct. Either there should be a point here or there should be a point here.
Correct.
Which will, yes, that's right. Yeah, it should be either here or here, such that this whole side.
For example, if you take a vertex, right? So then it does not work, right? And does not work.
If you take a vertex.
If you take a vertex, so then you don't get and, right? So one thing will work.
Yeah, true. Yes, that is correct. Yeah.
Right.
Yeah, this is actually or. Either there's a point here or here such that you can actually take the length of the, take the whole side and then within C, this whole side is there. So said otherwise, yeah, you can also talk, well, I think I'm out of time. You can also take a ball and actually see that the C ball contains, the other side. So that's the property that was observed of hyperbolic triangles, and then this was generalized to hyperbolic metric spaces, and Cayley graphs of groups which satisfy this are called hyperbolic groups, etc. So more about that. So I'll stop here today. If you have any questions, you can ask.
Yeah. So thank you very much for the nice talk.
Thanks.
Okay. Any questions?
Glad you liked it. Yes. So others, if there are questions, you can ask. If not, we can stop here.